Let's wait for a couple of minutes, see if others are joining. Then we'll start. All right, I think will start now, and if anybody joins, they'll join in between. So, good evening. My name is Umair Hussain. I'm a PhD scholar at the Department of Mechanical Engineering at IIT Madras, and I welcome you again to the sixth doubt session of the course of finite element method from variational methods to computer programming. So, until the last 5 weeks, we had discussed the basics about variational methods, variational principles, and then we extended the discussion to the finite element method, and we discussed the basic steps involved in the FEM problem, and then we started with the basic 1D FEM problems. So. We extended the discussion to basic structural problems in FEM. We discussed the 1D bar problem, we discussed trusses, and then we discussed beams. And finally, we ended the discussion by studying about the generalized frame elements that covered everything we had studied in 1D structural problems. So now I think by this the discussion on 1D FEM has been concluded, and we are going to start the 2D FEM problems from next week. So, but before going on with 2D problems, there is a need to for a better for a quick revision of basic calculus, basic tensorial calculus in order to easily derive the equation, especially the weak form for 2D problems. So, we'll quickly discuss what had been done in week 6 course content, and then we'll move on to discussing some problems. So, firstly, we'll start with initial notation or indexes of any quantity. So, if we are representing some variable as a, so the I the subscript I of the a is an index. So these indexes are of two types. First, we have free index, and then we have dummy index. So I've already written down here. So free index means if an index occurs only once, then it's called a free index, and the free index represents the order of tensor. And if the dummy index is when any index occurs twice, and it represents a summation. And there's a rule that more than the repetition of any index is not allowed more than 2 times. So it can occur either once or twice. So an example, so this summation convention is also known as Einstein summation convention, and an example of this can be understood using the dot product. So a dot product of two vectors is the multiplication of their respective components and summation of the product of their respective components. So which is u1 v1 u2 v2 plus u3 v3. If u1 u2 u3 are the three components of the vector u, and so this u1 v1 plus u2 v2 plus u3 v3 can be directly written as ui vi. It is actually summation using the sigma symbol. We can write as u equals to 1 2 3 and ui vi. Essentially means same. So we can just drop off this symbol and we can simply write it as ui vi. Sorry, simply we can just drop this and we can just simply write this as ui vi. So this essentially means this. So yeah, so we have discussed that, what is free index and what is the dummy index. So if we have a any some tensor in this form aijj. So here I is the free index and j is the dummy index. So this overall quantity is a first order tensor, or which is also known as a vector. So we can simply write this a summation of ai 11 plus ai 22 plus ai 3. Assuming that this summation is over the three dimensions, then we can conclude to three. Otherwise, in some cases, it can be more also, or just till just two also. So by default, we assume it to be just three. Then yeah, we move on to vectors. So it's the definition of the vector. I think we had studied a long time ago that vector is any quantity that has a magnitude and a direction. So so the basis basis of any vector represents its direction. So it consists of two components of I mean a basis and the components of basis. Usually, the basis by default that we consider are the nominal basis. That is E1 equals to 1, 0, 0. That we can say is the x-axis. E2 equals to 0, 1, 0. That is the y-axis, and E3 equals to 0, 0, 1. That is z-axis. And we can use their linear combination to get any vector in that 3D space. If we have three components, then we can say the dimension is 3 or 3D. We can have more than three dimensions also, but then we'll have to change the basis. So we can have some basis like 1, 0, 0, 0, 0, 1, 0, 0. Like that, we can have four bases also, and so on. So in general, we know what a uh, basic vector is. And to get any component of the vector, we just take the dot product of the vector with the respective basis. We get that component. So if we take a dot product of the vector by if the basis e1, we'll get the component u1, right? Because we know this property that e1 dot e1 or ei dot ej equals to 1 if I equals to j, yeah, and 0 if I is not equal to j. So then we have so using this property only we define something known as Ronica delta. So Ronica delta is a second order tensor because we have two free indexes I and j. So the property of Ronica delta is that it is 1 whenever I equals to j and 0 whenever I is not equals to j. So it basically, we want to write it in a matrix form, that is a unity identity tensor, identity matrix, whatever you want to call it. So as mentioned before, this should be the definition of Ronica delta. And one interesting property of Ronica delta is that it acts as a substitution operator. So if we have any, so if we have any quantity with any indices, then we multiply it by the Ronica delta. So it substitute the index. So if we have over here, so if you say okay, I'll write different one. We have km, so we can use it to substitute this one. So this k can be substituted with the m. So this will be equal to bij. So this is the property substitution property of the Kronecker delta. And then next we have a permutation symbol, or it is also known as Levi-Civita symbol. So this is defined as the cross product of the basis Ei Ej. So this is the actual definition of Levi-Civita symbol. So uh, the definition actually involves that if this I, J, and K are in cyclic order, uh, I, J, and then K. Sorry, I, then J, then K, then I. If this cyclic order is maintained in the substituting this, replacing these I, J, K, then it gives one. So if we have 1 2 3 2 3 1 3 1 2, it gives one. But if this cycle is disturbed, if it's in opposite direction, then we get minus one, and rest all other entries are zero. If so, if any or either of the ijk or ki is same, then we get zero. Now there is an identity that can help us to change from Levi-Civita symbol to Ronica delta, and that is this. So if two Levi-Civita symbol are multiplied with just one common index, that is, say if they have same I, then we can transform it into the Ronica delta. So we have ijk epsilon ijk into epsilon imn, that gives us delta. Since I is a dummy index now, so I can be so in order to maintain the order of the tensor, I can be removed, and we have delta jm delta kn minus delta jn times delta km. Then we have a scalar triple product, which is defined as this. So, in writing in terms of initial notation, this can be written as this: ui vjwk time epsilon ij. So, a triple product can be written in terms of the Levi-Civita symbol. Next, we have a second order tensor. So, a second order tensor, in general language, we also call it as a, a any quantity which has two directions. I'm interested in two directions. One is the direction of the quantity, and another is the direction of the plane over which it is applied. But in talking in terms of more mathematically, then it is actually any quantity that maps a vector to another vector, or it can also be called a linear transformation. This is basically a matrix, what we know as matrix in general terms. So a matrix T, if multiplied by a vector U, will give another vector V. So this can be written as T I j U j equals to Vi in terms of initial notation. Next, so we have we already know about the dot product, the cross product. So dot product basically reduces the order uh, of the tensor, and cross product, it actually cross product of any two vectors give you the another vector in another direction, that it maintains the order of tensor. Then we have a tensor or dyadic product, which is represented by this symbol x in a circle. So it basically increases the order of tensor. So order of the tensor. So if we multiply if we take the dyadic product of two vectors, we'll get a tensor. Even the basis of any we can represent any the components of a matrix in terms of their basis as a dyadic product. So ei ej are the vector are the basis for a vector, like we discussed before, like this 0 1 0 0, like this. So if we take diagonal product of this, suppose this is E1. So if we take the direct product of E1 with itself, we'll get a matrix like this. So this basis would represent the T11 component of this matrix. You can write it T11 into E1 direct product with E1. This is the first component. Likewise, we can have more components in this way. The way to take the direct product is we multiply the column with a row. So if we multiply this, we'll get this matrix. 3 cross 1, 1 cross 3. And then next we move on to the gradients. So a gradient of any quantity basically will increase the order of tensor of that quantity. So if we take a gradient of a scalar function, we get a vector, and we so first we should know what this del operator is. So this del operator means dou by d dou x of any quantity with the basis e1 plus dou by dou y times basis e2 dou by dou z basis e3. Or we can, in simpler term, we usually represent x1, x2, and x3. So to represent different directions. So all gradient divergence, whatever we have, all these are the derivatives with some order change of the tensors. So the gradient of any scalar function can be defined as this. And if we have if we take gradient of a vector, we get a matrix or a second order tensor. Then we have divergence. So divergence of any quantity is the dot product with this del operator. This is known as del operator. So if we take dot product with this del operator, then we're basically reducing the order of the tensor. So if we take the divergence of a vector, then we get a scalar. And if we take the divergence of a second order tensor, we get a vector. Then we have curl. So curl basically maintains the order of the tensor. So we take the cross product with this del operator here. Then we have the Gauss divergence theorem. So Gauss divergence theorem basically is used to transform the integral from the surface integral to the volume integral to a surface integral. So if we have the domain of volume omega, we can transform the integral to its surface. So this basically is useful whenever we know the information on surface. Sometimes it's easier to calculate any information on the surface. Then we can get the information in the entire volume here, or vice versa. So so if we have some gradient, if we have a volume integral of any gradient of any function, then we can transform it to the surface integral. So this is actually useful in getting the weak form in 2D problems. So if you remember that we used to do perform integration by parts in 1D problems to get the weak form. Here instead of that we can use the Gauss divergence theorem to do the same thing. So suppose if we have some quantity this and we take the divergence of this, then by applying the cross product rule, the product rule of differentiation, we have these two quantities. So we can say that this quantity can be written in terms of these two quantities. So if we have some in our strong form, we usually have a second order derivative, something like this, and we usually multiply it with the weight function. So to evaluate this term here, we replace it with the other two terms. So now we have this term and this term. So here we have the divergence of this whole term. Then we can apply the Gauss divergence theorem here, and we can change it to a surface integral. So this is usually what we are left in the weak form. We have a volume integral term with the reduced differentiability. So we have reduced the differentiability from the our primary variable t here, yeah, and then we have another integral term with the reduced order, or we have from volume integral we have reduced it to surface integral. So that was all that we had discussed in this week's content. And so the main purpose of this, if you'll see, that is to get to the point where we can easily derive the weak form of 2D equations, 2D strong form equations. So we'll wait for some time now and see if anyone comes and ask any question. Then we'll discuss some problems related to whatever we've discussed here. Sorry. Okay, I think now it's time to move on to some problems. So we'll discuss some problems related to tensor calculus and maybe something uh, that we had done in previous weeks. Okay, so problem number one. What is the order of tensor for the following expressions? So remember that in the initial notation, we have two types of index. First is the free index and second is the dummy index. So out of the two, the free index is the one that represents the order of tensor. So we need to determine the free index, and the number of free indices would tell us the order of tensor. So first one we haveCijkl. So do we see any repetition of any index? That is no. So we don't have any dummy index here. So we have all four I, J, K, and L as the free indexes. Free indices. So we have the order of tensor as 4 here. Then next we haveCijkl epsilon KL. So here we see the repetition of K and L. So both K and L are dummy index. So we have only I and J as the free indices. So now the order of tensor is 2. Uh, we can also expand this as we can also expand the dummy indices here. You can write this as, so we'll assume 3 dimensions. Now next we expand the L. So for each of these terms we'll have three terms each. We'll have total 9 terms. J 1 1 epsilon 1 1 plus Cij 1 2 epsilon 1 2 plus Cij 1 3 epsilon 1 3. Then we expand the second term. We have Cij 2 1 epsilon 2 1 plus epsilon C. Then we have Cij 2 2 epsilon 2 2, and we have Cij 2 3 epsilon 2 3. Then we expand the third term. We have Cij 3 1 epsilon 3 1 plus Cij 3 2 epsilon 3 2 plus we have Cij 3 3 epsilon 3 3. So we'll have so this is one whole big quantity. Uh, then we still have I and J as the free indexes. So we have, so this whole group of bunch of terms represents second order tensor each. Then we have sigma ij, Cij, Kl, epsilon Kl. So here K is repeated, it's a dummy index. L is repeated, it's a dummy index. Then we have I also repeated and we have J also repeated. So all are dummy indices. So this is a zeroth order tensor. So if we keep expand it like we expanded it above, we have a one big bulky expression. That is, so the number of terms would be, I think, 3 to the power 4 there. that is 27 terms. So that's a scalar. This is a scalar quantity now. Then we have Aij, Bjk, and Ckl. So here we see that J is repeated and K is repeated. So J and K are dummy indices, and we have I and L as free indexes. So we have the order of tens is 2. We have 2 free indices. Then we have Aij and Bji, Ck. So I is repeated, J is repeated. So I and J are dummy indices, but K and L are not repeated. So we have 2 free indices here. Again, the order of tensor is 2. You can also try to expand this one here. We'll have A1J, BJ1, CKL. We'll just expand the other two terms. CKL is obviously common to all. So A, sorry, will be plus A2J, BJ2 plus A3J, BJ3. So we expand the first term again. A11, B11, A12, B21 plus A13, B31. Then we expand the second term, A21, B12 plus A22, B22 plus A23, B32. Then we expand the third term, A31, B13, A32, B23 plus A33, B33. And now above all this we have common CKL. Okay, so this was the first problem. So by just looking at the indices of any quantity or even the product of multiple quantities, we can tell the order of tensor. It's that easy. Now we expand the following expressions. So for first part we have delta ij, delta ij. So there's an interesting property of the Aronica delta that it substitutes the index of the any quantity to which it is multiplied to. In this case, the Aronica delta is multiplied to another Aronica delta, so we can easily switch the indices here. So we'll use this to switch the j here. So we'll switch the j here with I. So we have delta I. So delta IA is so now it becomes a dummy. So IA is already a dummy index. So we can expand it using summation convention as delta 1 1 plus delta 2 2 plus delta 3 3. So we know if I equals to j in delta ij, then it is 1. Otherwise it's 0. So all three terms will give us 1. We'll have the answer is 3. Now next we have delta ij, delta jk, delta ki. So we apply the substitution property from here to here first. So we have delta ij times delta k can replace by I. So we have ji. Now again we can do the same here. Substitute, we get delta I again. So which is again equals to 3. So we could have just did this first, then we would have delta ik, then again ki would again give us ia or kk. That's same. Next we have delta ij times delta jk. So here we can again replace this, we get delta ik. And So it is completely normal if we can change any index to another index if it's not they already present in the equation. So instead of k, we can also write it as j, I j or j k. It's all the same. So this ultimately gives us a second order tensor. It can be this identity tensor. Then we have delta ij into aik. So here we apply the substitute rule on the I index of A. So we get this as A J K. Okay. So here again we have, since there was I was the dummy index, we'll have again we'll say have the same second order tensor here. Okay. So this is how we apply the Ronica delta, the substitution property of the Ronica delta, and expand any expression. Okay. Now let's move on to the third problem. So we have to expand the following expressions. So first we have epsilon 3jk times aj ak. So first of all we start expanding by expanding j. So we have epsilon 31k a1 ak plus epsilon 3 2k a2 ak plus we have epsilon 3 3k a3 ak. Now we know the property of the epsilon or the Levi beta symbol, that if any index is repeated in the three indices, then it becomes zero. So this whole term would go to zero automatically. We are left with two terms here. So now we go on to expand the k index. So again we have first epsilon 3 1 1 a1 a1 plus we have epsilon 3 1 2 a1 a2. Then we expand the next second term. We have epsilon 3 to 1 a2 a1 epsilon 3 to 2 a2 a2. So firstly again this term goes to 0, so it's repetition not allowed in Levi simple. So I mean not allowed, it's allowed but it becomes 0. uh, and again this term will also goes to 0. Now we have epsilon 3 1 2 and 3 2 1. So epsilon 312 can be written as epsilon 123 A1 A2, right? And epsilon 321 can be written as epsilon minus of epsilon 123 A A2 A1, because epsilon 123 equals to epsilon 231 equals to epsilon, yeah, 312, that is all equals to 1. So basically this term actually becomes 1. And again, then we have epsilon 321 equals to epsilon 213 equals to epsilon 132, that equals to minus 1. So we have epsilon 312 here as 1, this term, and epsilon 321 as this term, we have minus 1. So this becomes actually minus 1. So we have a1 times a2 minus a2 times a1. So this whole terms become 0. Okay, I hope that's clear. Next we have p epsilon ijk equals to, sorry, into delta kj. So now we have multiplication of the Levi-Civita symbol and the Kronecker delta. So we apply the substitution property. So we have epsilon I j, the k becomes j. So now if we have j as the dummy index, we can expand it, or whatever we do, whatever expansion we do, we'll always have a repetition here. So I11 plus epsilon I22 plus epsilon I33. Irrespective of whatever the value of I is, the other two index are also always same. So they will always be 0. So this whole term becomes 0. Or it's a 0 vector, you can say. If there are three components, it's actually a 0, like this, because we have we have one free index here, so it's a first order tensor. Now C part, we have epsilon 1 jk a2 tkj. So we expand the j and k dummy indices. So we can take a2 common, I guess. There's no need to repeat a2 again and again. Epsilon I1 1k tk1 plus epsilon 1 2 k tk2 plus epsilon 1 3k tk3. Okay, so this goes to 0, repetition allowed. We still have other two terms, so we expand the other two terms with k. We get a2 again common. So epsilon, so whatever we expand k here, so if k, whatever expansion is here, if k equals to 1, we have a repetition of 1, so that term goes to 0. If k equals to 2, then I mean, I'm talking about this term. So if k equals to 1, this term goes to 0. If k equals to 2, this term again goes to 0. Only k equals to 3 would give us a non-zero value. So we can simply write it as epsilon 1, 2, 3, t 3, 2. Similarly, for this term, k equals to 1, k equals to 3 will give us a 0 value. So we can just write it as epsilon 1, 3, 2, t 2, 3. So we're left with these terms, and 1 2 3 is 1, and epsilon 1 3 2 1 3 2 is minus 1. So we have a 2 times t32 minus t23. Since we don't know the nature of the uh, t tensor or t matrix, we just leave it to here. But if it was a symmetric matrix, then this term would again go to 0. So this is the scalar expansion here for part C. Then we expand the d part, epsilon 1 j k delta 3 j v k. So again we apply the substitution property. We left with epsilon 1 3 k v k, and we expand it. So since we already have 1 and 3 here, k equals to 1 and 3 will give us a 0 value. So we can directly write it as epsilon 1 3 2 vk, and 1 3 2 is minus 1. So we have minus of vk. So this is the final answer for this. I'm sorry, not vk. K equals to 2. So I have minus v2 as the final answer. Okay, uh, next let's move on to the next problem. So the fourth problem is, if aij equals to delta ij times bkk plus 3bij, then evaluate bij in terms of tensor aij and its invariant akk. So we start with the expression aij equals to delta ij bkk plus 3bij. So let's multiply the whole equation by the delta ij operator. So this becomes aii, and this becomes 3 times. So delta ij times delta ij, we have seen before that it becomes 3. Okay, 3bkk. And again we have 3 delta ij bij becomes bii. And it is fine if we can substitute I with k. 3bkk plus 3bkk. So by the way, this kind of repetition of kk is allowed because it's between a plus sign. So if so, still these expression terms would be considered separately. So k is repeated two times. That is fine here, and this is again repetition two times. It is not considered repetition four times. So these are two separate terms. Just for clarification. So we can write bkk as akk divided by 6. So we substitute this back to our first main equation. We have aij equals to delta ij, and bkk we have akk by 6. Then we have plus 3 bij. So we write this as 3 bij equals to aij minus delta ij akk by 6. So we have bij equals to 1 by 3 aij minus delta ij times akk by 80. So this is the expression for bij in terms of the tensor aij and its invariant akk. Sorry, there's something blocking my camera. Just a minute, let me configure my screen again. Let me just quickly exit and re-enter the meeting to get my camera working. Yeah, I hope this is fine now. Yeah, so discuss problem 4 and solve this this given problem here using simple tensorial notations and properties of the Kronecker delta. Okay, so now let us discuss some problems of the basic FEM 1D FEM that we had done so far. So I discussed this kind of uh, element 1D element problem where the elements are connected in this fashion, and we saw how to make the connectivity metrics for this kind of problem. But we haven't solved this problem actually. So now we'll try to solve it using our generalized FEM code. So use a generalized FEM code to assemble the elemental matrices for the following axial bar problem. Assume AE equals to 1, no body force, and a point load P equals to 10 acting on node 3 towards right. Find the displacement. So we have three elements here. We'll mark this element 1, this is element 2, element 3. So we have element 1 whose global nodes are 1 and 3. We have element 2 whose global nodes are 2 and 3. We have element 3 whose global nodes are 3 and 4. This is basically our connectivity matrix which we did last time. So this is a rigid plate. So whatever displacement it will have. So at displacement anywhere on this plate would be same. So that's why all the nodes are marked as node 3. So the governing equation for a bar problem is so F here is 0, A equals to 1, and we have load P acting here towards right. So we have basically this equation. It's not a very big deal. It can be directly solved here. Can get some solution as u equals to c1x plus c2. So it's a simple linear solution. So now first we get the weak form. Simply we'll write this form limit for any element x1 to x2. So we'll try to do it using MATLAB now. So let me first open MATLAB here, my system, and then I'll share the screen. Apparently there's some issue with opening the file. Let me see again. Let me refresh the page. I don't know, there's some issue with opening the file. Let me see. Let me download it and then upload it and try. So I'll just download it and then copy the code here. We'll first check if it is working. Is it able to read the functions? So are we missing anything here? Swift quadratic path. Can work with linear elements, I guess. Okay, we modified the function last time with a and e values. Okay, I'll add that. First, let's use linear elements. Keep a and e as 1. Hope that's not required in the load vector. Okay, I haven't shared my screen. Let me share my screen here. Okay. Okay, I hope that's visible. So let me enter the coordinate data. So we have 4 nodes in total. We have node 1 at, okay, I haven't mentioned in the problem. So let me just do that. Keep this at x equals 0 equals to 1. This at x equals to 2. So we have 0. 2 is also x equals 0. 1, 3 is x equals to 1 and 4 x equals to 2. So for element 1 we have 1 and 3. For element 2 we have 2 and 3. Then we have for element 3 we have 3 and 4. We have a decision boundary condition x equals to 0 at u equals 0 at x equals 0. So that is first node and second node. And then we have a Neumann boundary condition for node 3, right? So node 3 will add b equals to 10. Then we keep the same Gauss points and Gauss weights. B for us is 0 and K would be a 4 by 4. We have 4 nodes in total. Now our loop starts over the elements. So we'll have the K and F evaluated for each element, and the respective uh, K and F matrix would be added to the global matrix in vector. And then we apply the boundary condition. I hope there's no issue with that. I'll try and run and see. Okay, we have some issue here. Okay, okay. Okay, actually this code is written for 1D, sorry, linear, so the quadratic elements. So let's see if we can change it, or we'll just use the quadratic elements instead. Remove this. Now is check. Sorry, we have to change the index here also. Total 4 nodes, right? Yeah. So we have our f as 0010. That's expected. Then this is our. So since we have applied the listed boundary condition on node 1 and 2, so our row 1, column 1 would look like this. Sorry, row 1, column 1, row 2, column 2 would be like this. We will have only something left in the last two rows and columns. So this is our displacement, and this is reasonable because we are applying a load here at a load here, right? Yeah, we're applying a load here at node 3, so we'll have some displacement at node 3, and then we applied so the same displacement would be carried on to node 4. If we would have fixed node 4, we also see that if it's a fixed structure of node 4, we can add that part too. We'll have only displacement at node 3. 4 is 0. So we add that, and what will we get? So you see, we only get displacement at node 3 and no displacement on any other node. So this seems to be a reasonable answer. So there's definitely some issue with the MATLAB online. I'm unable to access my old files. So I don't think we'll be able to do this next problem. We'll discuss this at the end if we have some time. All right, so now we try to understand a little bit more about the del operator or the gradient and divergence. So so for first part we have given u as a function. 4x square y square. So we need to find the gradient of u. So gradient is nothing but dou u by dou x e1 plus dou u by dou u by dou y e2. Since we don't have any z component, we can skip that component. So dou u by dou x is 8x y square times e1 plus dou u by dou y is 8x square y. We get a function as 8xy y times e1 plus x times e2. Okay, so yeah, next we find the divergence of the gradient of u, or this is actually the Laplacian of u. Basically equals to dou square u by dou x square plus dou square u by dou y square. So we already know dou u by dou x is 8xy square. We again take another derivative, we have 8y square. Then we have dou square u by dou y square. We already know that dou u by dou y is 8x square y. We again take its derivative with respect to y. We get 8x square. We have 8 times x square plus y square. Then the next part we have u equals to x cube y. So again we take the gradient of u. We have dou u by dou x first component and then dou u by dou y as second component. So derivative of u with respect to x is 3x square y first component, then dou u by dou y is x cube. Again the Laplacian of u is dou square u by dou x square plus dou square u by dou y square. So taking double derivative of u with respect to x, we get 6xy. Then taking double derivative of u with respect to y, we get 0 because the power of y is 1. So we get finally 6xy, the Laplacian of u. Okay, so this is one problem where we understood the use of the gradient and divergence operators. Now we try to use our knowledge of the Gauss divergence and gradients and divergence to get the weak form. So first step in any weak form is to get the variational statement or multiply by the given equation with the weight function. So we have there's no derivative involved in the second term here. We can leave it like this. But first term we have two derivatives on the t variable. So we need to transfer one derivative over the weight function. So if we'll perform if we'll apply the product rule and perform the apply the Gauss divergence theorem, we can do it like that. But I prefer it using the short method. Directly write it as. So first we write the volume integral term with minus sign, and we transfer this del operator on the weight function. We have gradient of w dot product with whatever we have with the other way. So this is one term. Next we will have the boundary integral term with plus sign. So here we'll leave w as it is, and we'll have this other term with removed del operator and dotted with the normal vector to the surface. This n actually represents the normal to the surface. So basically, whenever we define a flux to a surface, it is a normal to with respect to a surface. And then we have our other terms, which we did not touch. So we can write this as so gamma represents the boundary of the domain omega. We can, if we have the boundary condition defined, we can just substitute this term here with the given boundary condition, the Neumann boundary condition. So this gamma becomes zero wherever the Dirichlet boundary condition is specified, and will have some value wherever the Neumann boundary condition is specified. So this is our bilinear term, and all this is our linear term. Okay, so this is how we find the weak form. Okay, so let's move on to the next problem. So we have a differential equation of this kind. we need to find the weak form for this. I think the typing error here, we don't have any k and minus sign repeated. Okay, so again, first thing is multiplying by a weight function. So again, we apply integration part by parts or whatever Gauss divergence on the second order terms, second order derivative terms. This one, this one, this one, and the last term we leave it like that. So we have, sorry, for the first term, we have dou w by dou x transferred on w times dou u by dou x dx plus whatever boundary term we would have. We leave that. Then for second term, we have again same integral dou w by dou y dou u by dou y should keep the integral limits general, or it's actually minus sign, minus the boundary terms. Then again for third term we have integral dou w by dou y dou u by dou x plus boundary term. We'll not write this time. Then again we have this last term as it is, w time f d omega equals 0. So this can all be combined and written as dou w by dou x dou u by dou x plus dou w by dou y dou u by dou y plus dou w by dou y dou u by dou x equals wf d omega plus we have any boundary terms. So this would be our weak form. So this would be our, it is linear though, but would it be symmetric? It's bilinear, right? So the linear term. So it turns out that it will be symmetric. No, it won't be symmetric because of this term. So if we replace interchange w and u, we'll have dou u by dou y and dou w by dou x, and that's not same. So it turns out that this the stiffness matrix for this term would be a non-symmetric matrix. So we have the given weighted residual statement comes the strong form of the model equation shown below. So this is actually the strong form, and this complete thing is the weighted residual statement. So here we have defined f1 as c1 dou u by dou x plus c2 dou u by dou y, and f2 as c3 dou u by dou x, c4 dou u by dou y. and C1, C2, C3, C4 are constants. C3. So what should be the differentiability of W at least? So we'll just use one term here. W times we have dou by dou x of F1 is C1 dou U by dou x plus C2 dou U by dou y. And we just take this term alone. We'll need to transfer a differentiability on W by applying integration by parts. So we'll ultimately get as W by dou x and C1 times dou U by dou x. So W should be at least differentiable once. So it should be of C0. It should be continuous. We have a C0 continuity. So any linear function would be fine for this. For this kind of problem. Then we have a last problem. So derive the constitutive relation for linear elasticity for the isotropic material constant asCijk equals to lambda times delta Ij delta Kl mu times delta Ik delta Jl plus delta Il delta Jk. So the stress strain relation is equals to is given by the Hooke's law. We remember. So for 1D simple case, it used to be C equals to E times epsilon, where E is the Young's modulus. But for generalized stress and strain, for the multi-dimensional, multi-axial stresses and strains, we have this equation. SoCijkl is a so complete set of all material properties. So since it's a I is a fourth order tensor, so the so there will be I think about 81 constants to define this. So anyway, but because of different symmetries and applying isotropic case, we are reduced to just two parameters, lambda and mu. So this can be replaced by this equation. So we'll replaceCijkl by lambda times delta Ij delta Kl mu times delta Il Ik delta Jl plus delta Il delta Jk. And this whole thing is multiplied by epsilon Kl. So we now multiply epsilon Kl by each. So we have lambda times delta Ij. Delta Kl times epsilon Kl would be epsilon Kk. Then we have mu times. So now epsilon Kl is multiplied by each of the two terms here. So first by delta Jl. So it becomes delta Ik times epsilon. So K can be, so L can be replaced by K. So sorry, J. Yeah, K J. First one, right? Yeah, L can be replaced by J in epsilon. And for second term, we have Ik. So I will K with IL. So then this becomes epsilon ij, and this becomes this mistake here. Okay, okay, it's jk. Chalo, made a mistake here. So this is actually jl. So this becomes epsilon ji. But we know about the strain tensor that it is a symmetric tensor. So epsilon ij equals to epsilon ji. So this becomes sigma ij equals to lambda times epsilon kk delta ij plus 2 mu times epsilon ij. So this is the constitutive relation for an isotropic case for the linear elasticity problem. So with this, we can conclude the session, and we'll meet again next time in the next session. So this will be on the coming Tuesday, where we'll discuss the content of week 7. Okay, thank you everyone.